you. So I would like at the end of this lecture to describe some joint work with Bhargav on what you might call a Riemann-Hilbert correspondence over p-adic fields. So let me begin just reviewing the classical Riemann-Hilbert correspondence. So let X be a smooth projective variety over the field of complex numbers. And I'm going to write X analytic for the underlying complex manifold of X. And you can study local systems, complex vector spaces on this complex manifold. So these are more concretely representations of the fundamental group of X, if X is connected. And well, first, just using the fact that Xn is a manifold, you can identify these with vector bundles on X analytic with a flat connection. But now Xn is not just any manifold, it's a complex manifold. And so any vector bundle with a flat connection in particular has a holomorphic structure. So you can think about these as holomorphic vector bundles on Xn with a flat connection in the holomorphic sense. And then Serre's Gaga principle tells you that if X is smooth and projective, there's no difference between holomorphic vector bundles and algebraic vector bundles. It actually can be identified. Algebraic vector bundles, and under that correspondence, the flat connection just goes along for the ride. So this is some incarnation of the Riemann-Hilbert, or sorry, now algebraic vector bundles on the original variety X. So this is some primordial incarnation of the Riemann-Hilbert correspondence, and it's been extended in a number of ways. So one extension is something that Pierre did in around 1970, I think. We removed the word projective here. So now let's just say X is a smooth algebraic variety over the complex numbers. There's a similar correspondence here. Now it's no longer true if X is not projective that every every holomorphic vector bundle has an algebraic structure. But what Pierre showed is that if you have a holomorphic vector bundle with a flat connection, it might not have a unique algebraic structure, but it has a canonical algebraic structure, which is characterized by the requirement that the connection has what are called regular singularities. So these local systems get identified with algebraic vector bundles on X with a, let's say, flat regular connection. And 15 years later, this was extended further by Kashiwara. What I'm actually going to refer to as the Riemann-Hilbert correspondence. And I'm going to describe what's actually called the algebraic version of the Riemann-Hilbert correspondence, which is, I think, due to Bailynschen and Bernstein. It's a generalization of this. So local systems you can think of as sheaves of complex vector spaces on this manifold, which are locally constant. And the right-hand side is algebraic vector bundles, meaning sheaves of OX modules that are locally constant. And Kashiwara's generalization is to remove the word locally constant from both sides. So there's a similar correspondence if you want to work at the level of abelian categories. Reverse sheaves on this complex manifold identify with what are called algebraic D modules. X. I should add some adjectives here. Regular and holonomic. So regular means having regular singularities. It's an analog of that condition up here. Holonomic is some kind of finiteness condition. So an algebraic D module, I'll say a little bit more about this later, but you can think about this as a quasi-coherent sheaf on X, which has a flat connection. Note, you're just dropping the requirement that the thing that has a flat connection is supposed to be a vector bundle. Because there's an equivalence of abelian categories here, but it's better to state it as an equivalence of derived categories. So you can look at the bounded derived category of constructible sheaves of complex vector spaces on X, and this gets identified with the derived category of algebraic D modules that are required to be regular and whole number. Okay, this is a story over the complex numbers, and it identifies two categories where the category on the left-hand side is defined in a way that really uses the fact that a complex variety has an underlying topological space, using the fact that C has a topology and it gives you a topology on the set of complex points. But the right-hand side of this correspondence is something that's defined in a purely algebraic way. You could start with algebraic variety over any field of characteristic 0, and then, well, really over any field, and you can talk about sheaves with a connection, and it's a well-behaved theory over any field of characteristic 0, and there's this nice theory of algebraic D modules. And that gives you, so this correspondence gives you a purely algebraic way of accessing information about the category of sheaves on this underlying topological space. So what I'd like to talk about for the rest of the lecture is an analog of this statement when you're not working over the complex numbers, but you're working over fields with different kind of topology, something more like a p-adic topology. Let me make some definitions that are going to be in force for the rest of this lecture. So K, capital K, is going to be a field which is complete with respect to discrete valuation. The characteristic of capital K is going to be 0. And I'll write OK for its ring of integers. This has a maximal ideal, and this is going to be a perfect field of characteristic P. So the question is then, what can you say about having a correspondence like this if X is now a smooth variety? Wait, let me add one projected. But now it's going to be over this p-adic field K. Well, you can still talk about things like algebraic vector bundles with a flat connection on X, or more generally, algebraic D modules on X. And well, there's an analog of the left-hand side that you could consider, which is p-adic étale sheaves on the variety X. So the question that I want to say something about is, what is the relationship between p-adic étale sheaves on X and algebraic D modules? X. Leave this as a question mark, and I'll say something about it at the end. This is a question which has a lot of history. So I'm going to spend most of the lecture just talking about the history. So the first thing to observe is that this is an interesting question even when X is just a point. Right, so let's talk about that example. So let's say X is spec K itself. Is this category of QP étale sheaves is something interesting in that. So the left-hand side can be thought of as representations, continuous representations. the Galois group of K bar over K, QP vector spaces. And well, vector bundles with a connection on a point, that's not so interesting. These are just finite dimensional vector spaces over K. So these categories are not going to be equivalent. The category on the left-hand side is, for example, quite a bit more complicated than the category on the right-hand side, but you could nonetheless ask how they are related. So let me begin with a very naive attempt that you could make to relate them. Just a construction which goes from the left-hand side to the right-hand side. Let's say you start with some QP vector space having an action of the Galois group G, and you want to extract a K vector space from it. Maybe the most obvious thing you could do is take V and tensor it over QP with an algebraic closure of K, and then take the Galois invariance inside that. That's a construction. You input an object on the left-hand side, you get out an object on the right-hand side, and probably this just gives 0, right? There's no reason that when you tensor V with K bar, that it has to have any Galois invariant vectors at all, or any non-zero Galois invariant vectors at all. You can slightly improve this construction. Let me write C for the rest of this lecture is going to be a completed algebraic closure. Field K. The completion of K bar with respect to its C-adic topology. That gives you a slightly better chance of having some invariant vectors. And it's not hard to convince yourself that this is a finite dimensional K vector space whose dimension is bounded above by the dimension of V, but usually it's smaller than V. So this is a vector space of the same dimension, I believe, if and only if V is a potentially unramified representation. So representations that you're interested in practice are not going to be seen by this construction very well. So what kind of representations are you interested in practice? So let's think about Galois representations that come from algebraic geometry. So let X be, again, a smooth projective over field K. And then you can take your favorite cohomology group of X base change to this completed algebraic closure. Let's say with QP coefficients. And this is something that will naturally carry an action of the Galois group G. So this is a typical example of something that lives on this category on the left-hand side. And now this naive construction, what you're doing here is you're hoping that you start with some complicated representation of the Galois group. And when you tensor with C to make it into a C vector space with a semilinear Galois representation, that it becomes simpler. And for representations like this, that is the case. So let me state this as a theorem. That if you take Hn of xc, coefficients of QP, after you tensor it with the field C, this has what's called a Hodge-Tate decomposition. This splits as a direct sum over I plus j equal to n of hi of x with coefficients in differential forms of degree j. So this is a K vector space and base change to C and with an appropriately added Tate twist. So what this is saying is this Galois representation, once you tensor it to C to make a semilinear Galois representation, it becomes kind of simple. it's not something that necessarily has a basis of Galois invariant vectors, but it looks like a direct sum of pieces of Tate twists of representations of that form. So maybe just a bit of history. So this is a theorem of faultings from the 80s, but this was conjectured by Tate in the 60s. And Tate proved this in the special case where X is an abelian variety with good reduction. And so it's called the Hodge-Tate decomposition because it looks kind of like the Hodge decomposition in complex geometry, and because Tate was the one who essentially discovered it. So motivated by this, let's make a definition. So V, a Galois representation, is Hodge-Tate. If when you tensor over QP with C, this splits as a sum of Galois representations of the form C Tate twisted by n for different values of n. So then part of the content of this theorem of faultings is that if you look at the Étale cohomology of a variety over K, base change to C, it gives you a Hodge-Tate representation in this sense. And it's also a construction. If you have a Hodge-Tate representation, I think the Fontaine's notation for this was D Hodge-Tate. B, a K vector space, which is given by the following construction. You take the direct sum over all integers n, or why don't I say over all integers j, of V tensored C Tate twisted by j, and take the Galois invariance inside there. So here the input is a QP representation of the Galois group, and the output is some graded vector space over K. And this theorem is telling you also what happens when your Galois representation comes from geometry. This outputs the graded vector space, which is just the direct sum over J of coherent cohomology of X with different coefficients in differential forms of degree J. Now, this is not quite what you might want the Riemann-Hilbert correspondence to do. The Riemann-Hilbert correspondence, what you would want is something where you put in something that relates to Étale cohomology and it outputs something having to do with de Rham cohomology. So here you're inputting something having to do with Étale cohomology, and it's outputting the Hodge cohomology of your variety, or the associated graded for the Hodge filtration on its de Rham cohomology. So this picture is something that you might want to upgrade. To a story about de Rham cohomology, and the appropriate formulation of that was introduced by Fontaine. So Fontaine introduced a ring or a field, the field of p-adic periods. Let me tell you a little bit about how this field V de Rham works. So first of all, this is a field which carries an action of the Galois group G. K sits inside here as the subfield of G invariant vectors. The field B de Rham has a discrete valuation. The valuation ring is usually denoted by B de Rham plus. And inside B de Rham plus, you have its maximal ideal, which is a principal ideal. And B de Rham plus modulo M is this completed algebraic closure of K. And moreover, more generally, for every n, you can look at the maximal ideal modulo the maximal ideal. So to the power n modulo the power n plus 1. This is a one-dimensional C vector space, which is identified with the nth Tate twist of C as a Galois representation. So B de Rham is equipped with a filtration by powers of this maximal ideal, and the associated gradient of that filtration are exactly these Tate twists of C that appear when you start thinking about the Hodge-Tate decomposition. So another theorem of Falting's is an upgrade of the previous theorem to a statement about what happens when you take the étoile cohomology of a variety and tensor it over QP, this field B de Rham. This gets identified with the de Rham cohomology of your original variety X. So this is a finite dimensional vector space over K, tensored with B de Rham. And this is a isomorphism of, well, B de Rham vector spaces with the Galois action. And moreover, it's an isomorphism of filtered B de Rham vector spaces, where on the left-hand side, you just give it the obvious filtration coming from the M-adic filtration of B de Rham. And on the right-hand side, you give it a filtration, which is the tensor product of the obvious filtration on B de Rham with the Hodge filtration on de Rham cohomology. And with respect to that, this is actually an isomorphism of filtered vector spaces. And if you take the associated gradient of this isomorphism, you recover the previous theorem of Falting's, the Hodge-Tate decomposition of the cohomology of your variety. Okay, so I think in order for the end of my lecture to make sense, I'm going to need to tell you a little bit more about this field B de Rham. I need to tell you how it's constructed. So I feel like this is the kind of thing in a talk that pleases no one, because either people already know this well, or it's just going to seem completely mysterious. And for those of you who find this completely mysterious, it was completely mysterious to me for many years. So I commiserate. Okay, so let me just say a few words about how this field B de Rham is constructed. Okay, so the essential point is that, so inside this completed algebraic closure of C, there's a valuation ring, which I'll denote by OC. And the input is going to be that OC is a perfectoid ring. General construction that you can do, you can apply this to any ring if you want. You can take your ring, you reduce it mod P to get an FP algebra, and then that has a Frobenius endomorphism. So there's some map from OC mod P to itself given by raising elements to the P power. Take the inverse limit of sequence of copies of OC mod P, transition maps given by the Frobenius. And that's a ring denoted by OC flat. And now this, by construction, is a perfect FP algebra. So it has a canonical lift to characteristic 0 given by taking the ring of Witt vectors. And well, this ring of Witt vectors has a universal property in this context. This has a map to OC flat and therefore a map to OC mod P. And this will automatically lift to a homomorphism back into OC. This uses the fact that OC is p-adically complete. And now one of the first lemmas that you prove in the theory of perfectoid rings is that if OC is a perfectoid ring and you run these commutative algebra constructions, that this map is a surjection with kernel the principal ideal, generated by some element D, and D is not a zero divisor. So this ring is typically denoted by A-inf. So what does this mean? Well, if you take this ring, your valuation ring OC, that's what you get by taking A-inf and reducing it mod D. But more generally, you could take A-inf mod D squared, or A-inf mod D cubed, and so on. This forms an inverse system whose limit is A-inf. But now OC is the valuation ring in this p-adic field C. So this embeds into C, and similarly, this embeds into A-inf mod D squared with P inverted. C is what you get by taking OC and inverting P, and you can do that to every stage in this inverse system. Take this p-adically complete ring and invert P, and now B de Rham plus is defined to be the inverse limit of, sorry for my terrible board work, the inverse limit of this system here.
It looks like it's
What's that? It looks, yeah. If you change the side that it appears on, okay, so this constructs for you a ring which surjects onto the field C. And it's not hard to convince yourself, if you believe the statement that I made here, that this B de Rham plus, first, the image of D in B de Rham plus is a non-zero divisor. And if you mod out by D, then you get the field C. And moreover, B de Rham plus is d-adically complete. So that means that this is a discrete valuation ring with residue field C. And B de Rham is defined to be what you get if you take B de Rham plus, and instead of modding out by D, you invert D. Okay, so that's the construction of this field of p-adic periods. And I'm showing you the construction just because I want to call attention to one feature of it, which is that it's a construction that you can do anytime you have a perfectoid ring. So the usual B de Rham plus is what you get when you apply this construction to the valuation ring in a completed algebraic closure of K. But theory of perfectoid spaces gets a lot of mileage out of considering this construction more generally. All right, so so far I've been talking about what you might call the Riemann-Hilbert correspondence over a point. So let me just actually spell this out. So how long have I been talking? Not that long. Okay, so definition. So let B be a the QP Galois representation. Is called a de Rham representation. If, well, if you tensor V over QP with B de Rham and take the Galois invariance, so this is going to be a K vector space. One can show that this is a finite dimensional K vector space whose dimension is always at most as big as the dimension of the original representation V. And we say that V is a de Rham representation if equality holds. That's the same as the QP dimension of V. Or another way of saying it is V is a de Rham representation if after you tensor with this ring of p-adic periods, you can find a basis of Galois invariant vectors. And now, in this case, you'll define, well, actually, why don't I call it RH to be evocative? Useful Riemann-Hilbert correspondence. The Riemann-Hilbert correspondence in this setting should take this Galois representation V and assign the K vector space given by the right-hand side over there. In this case, so that's a bit of terminology. If you grant this bit of terminology, then you can restate what Falting's theorem was saying. Falting says that if you look at the QPA cohomology of your smooth proper variety X, first of all, this is de Rham representation, and if you apply RH to it, what you get is identified with the analogous de Rham cohomology of X. Okay, so the question is, how does this generalize to varieties which are more complicated than one? So this is the Riemann-Hilbert correspondence over spec K, not over X. I'm applying it to a vector bundle that comes by looking at the cohomology of X. So this theorem was upgraded by Pedro Scholze about 10 years ago to a statement about local systems not over a point, but over a variety X, or more generally, a rigid analytic space X. I'll stick to varieties just for the sake of definiteness. So let X be a smooth projective variety over K. So Scholze introduced a class of QP local systems. X that he called de Rham local systems. And definition of de Rham local system is rigged so that when you specialize to the case when X is a point, it becomes the notion of a de Rham representation in Fontaine's sense, in the sense of the definition that I just gave. And he introduced a functor, which goes from de Rham local systems on X. And assigns vector bundles on X with a flat connection. So this is construction which is analogous to what over the complex numbers is the sort of primordial version of the Riemann-Hilbert correspondence, when everything is smooth. The input is something that is a local system on a smooth projective variety. I guess he actually worked in the rigid analytic setting, and it was local on the rigid space. But if you want an algebraic statement, X has to be proper. And while I'm not going to review his construction, and the definition of de Rham was essentially write down the construction. The local system is called de Rham if the construction works. That is, given an arbitrary local system on X, there's something that you can write down that kind of looks like it should be a sheaf with a connection on it, but it's not necessarily a vector bundle of the right rank. And if it is a vector bundle of the right rank, then you call the local system de Rham. And that's a little bit of an unsatisfying picture because maybe the class of de Rham local systems is quite small, but follow-up work of Liu and Zhu showed that actually that's not true, that this condition that Schulze introduced of being de Rham is something that's quite often satisfied. So what their theorem says is let E be a QP local system on X. Let's say X is connected for simplicity. The following conditions are equivalent. One is that E is de Rham, meaning that Schulze's construction works and associates to E an algebraic vector bundle with connection. Two is that stock of E is a de Rham-Galois representation. For every closed point. Variety. And condition 3 is the same thing, but just at your favorite point. Closed point X and X. So this condition of being a de Rham local system is actually not really any stronger in the case of a high dimensional variety than it is in the case of a point. It's just saying something about demanding some condition on the Galois representations that you get by taking the stalks of your local system at the closed points. Okay, so this is something that you might call the analog of the Riemann-Hilbert correspondence for local systems. And what I would like to do for the rest of this talk is tell you about a different construction, which is equivalent for local systems, but which makes sense for more general kinds of QP étale sheaves on X.
There's no filtration.
Yes, sorry. This produces filtered algebraic vector bundles with a connection satisfying Griffith's transversality. So this is going to be essential to the construction, to the generalization of this construction that I'm going to describe. We're really going to take advantage of the fact that we're not just supposed to produce D modules in non-Archimedean geometry. You're supposed to get filtered D modules. So this is really something that I think is very different in the non-Archimedean and the Archimedean stories. So in the Archimedean world, there's a story of the Riemann-Hilbert correspondence, which relates constructible sheaves to algebraic D modules. And there's Hodge theory, which tells you that often the D modules that you meet carry filtrations. In the Archimedean version of the story, the Riemann-Hilbert correspondence is going to produce the filtration as well as the D module.
But also you start over K, not over C.
What's that? Yes, exactly. And well, if we're over C, there's a construction which is going to give you something, but it's not even going to be a flat connection. let me stick to K. So I want to take the last, what have I got, 20 minutes of the lecture and tell you about an extension of this construction. But first, I want to go back and address a sort of technical point. So just remark. So this is a construction which works at the level of abelian categories, right? But the Riemann-Hilbert correspondence of Kashiwara was some equivalence of derived categories of construct. Left-hand side was some constructible derived category, right-hand side was a derived category of B modules. And so let's say we are aiming for a construction which works derived categories. And so let's just go back to the case where X is a point. And in that case, I told you what this construction is supposed to do on a Galois representation. You're supposed to take your Galois representation, tensor it with the field B de Rham, and take Galois invariance inside it. In other words, you define this to be H naught of the Galois group with coefficients in V tensored over QP. This is not a construction which is friendly to working with derived categories, because here it's an H naught, and there are potentially other cohomology groups. And actually, there aren't just potentially other cohomology groups, there are other cohomology groups. So let me just remark that in this setting, we looked at H1 of G acting on V tensor over QP B de Rham. This is another K vector space of the same size. So just taking H naught is maybe not a construction which makes sense at the level of derived categories. An analog of that you might try is to take the derived version of G invariance in V tensor over QP B de Rham. But this would actually be a different construction because it would see the higher cohomology of G acting on this vector space. And well, cohomology above degree 1 vanishes, but cohomology in degree 1 doesn't vanish. So a related technicality in working with these constructions is that the class of de Rham representations is not closed under extensions. And so I just want to address this point. What's the problem? So there's a calculation. It goes back to Tate, that if you take H1 of your Galois group acting on a completed algebraic closure of K, this is a one-dimensional vector space over QP, meaning there's an interesting extension of, sorry?
K, right?
K, yes, sorry. One-dimensional vector space over K, meaning there's an interesting extension of C by itself as a continuous Galois representation. So what is that extension? Well, let me just tell you how you can describe it. You take a two-dimensional vector space over C with generators X and Y, and you let the Galois group act in such a way that the element X is Galois invariant. So that corresponds to like the element 1 inside this C inside question mark. And the element Y transforms by G of Y is Y plus the log of the cyclotomic character on G times X. So this is an extension. The trivial representation is a de Rham representation. This is an extension of the trivial representation of itself, which is not de Rham, because when you tensor this vector space with B de Rham, well, you can't necessarily get rid of the way the Galois group is acting on this element Y. The ring of p-adic periods is not big enough to see that when you tensor this with B de Rham, that it has a Galois invariant, sorry, it has a basis of Galois invariant vectors. But you can address this by working with a bigger period ring. So to fix this, I'm going to replace C by just a polynomial ring C brackets U, where the Galois group acts on C brackets U by declaring that an element of the Galois group acts on U by carrying it to U plus log of the cyclotomic character on G. So just take C and add something which looks like the Galois, enlarge it so you see this representation sitting inside it. Now let me make some definitions. So say that V is weakly Hodge-Tate. So V is some QP representation of the Galois group. If, well, let's take the same construction as before, where you take V, you tensor it with all the different K twists of C, and then take Galois invariance inside. But now let's actually just add this formal variable U. This is now maybe a little bit less obvious that this is finite dimensional as a vector space over K, but it is finite dimensional as a vector space over K. And in fact, that dimension is always less than or equal to the QP dimension. V is weakly Hodge-Tate if these have the same dimension, and they're always an inequality. So let me remark that it's an analogous notion of weakly de Rham, just defined in the same way, but using the de Rham period ring instead of this direct sum, but it's actually equivalent to the notion of being weakly Hodge-Tate. So this implies that if I take V and I tensor over QP with V de Rham, I'm going to add U, and here I'm going to put it in angle brackets to indicate that that's a completed polynomial ring. This applies to the G invariance inside here. This is a vector space of the same dimension. So let me call this RH of V. And moreover, this is compatible with my previous definition, what I called RH of V, that if V is a de Rham representation, then in fact the Galois invariant vectors inside here are all things that can be written without the U. Adding the U doesn't add any more Galois invariant vectors. But this class of weakly Hodge-Tate representations is a little bit bigger. It includes, for example, an extension of QP by itself, with the Galois group acting in this way. And another remark, which is a consequence of Tate's calculation that this is essentially the only cohomology class that you see, the one that's killed by adding this variable u, is that the collection of weakly Hodge-Tate representations is closed under extensions. Okay, so let me make a definition. So now let's go back to the setting where we have a smooth projective variety X defined over the field K. And now let E be a QP, constructible QP sheaf. So definition. Weakly Hodge-Tate. If the stalk of E at any point is a weakly Hodge-Tate as a Galois representation. Closed point X. And as in the Liouville situation, it's not really something that you have to check at every point. It suffices to check at a single point of each stratum on which, if you choose some stratification by connected subvarieties, on which this sheaf is locally constant. So this is some class of constructible sheaves, which is not everything, but it's pretty large. And now, so claim is a pointer. I'm going to call RH, where the input is constructible derived category of QP étale sheaves on X. And why don't I add a decoration here? The cohomology sheaves are required to satisfy this weakly Hodge-Tate construction. And it goes to the derived category of bounded derived category of regular holonomic D modules. And moreover, that this is compatible with all the usual operations on both sides. Push forward Faraday duality. And actually, it's a little bit better than that. And we're going to take advantage of the fact that it's a little bit better than that. It lands in the category of filtered derived category of DX modules. And many of these compatibilities are at the level of filtered D modules, like compatibility with Verdier duality, compatibility with proper push forward. That holds at the level of the associated gradient of the filtration. Okay, so almost out of time. So why don't I just tell you what the construction is?
So filter distinct, thinking that D itself is filtered.
What's that? D itself, yes, exactly. Okay. So let me tell you the definition of this functor. So we have our variety X, algebraic variety over K. It has an associated rigid analytic space, which I'll write as Xn. And there's various topologies you can put on that. You can give it the analytic topology, you can give it the étale topology. I want to give it a very fine topology introduced by Peter Schulze called the pro-étale topology. So I'll emphasize that by giving it a different name. Look at the pro-étale side of X. So here you have the usual sheaf of algebraic functions on X. The rigid analytic space has also a structure sheaf with a subsheaf of integral functions, which I'll write as O plus. And on the pro-étale side, these have completed pullbacks, which I'll emphasize that they've been completed by writing hats on top. And now, basic insight of Schulze is that this pro-étale site is something that really lets you treat X as if it's locally topologically very simple. Like in the world of complex manifolds, the analytic space of a complex variety is a locally contractible topological space. This thing is not quite locally contractible, but it has a lot of open sets that feel like they have the topology of Cantor sets. Another thing that is what I'm actually going to take advantage of here is that this structure sheaf becomes in some sense locally very simple. So X pro-étale N has a basis opens U such that if you take this completed structure sheaf and evaluate on U, this is a perfectoid ring. And this sits inside hat Xn of U without the plus. This map is just given by inverting P. And now let me remind you that this construction of B de Rham was something that makes sense for any perfectoid ring. So this receives a map from something that you might call, I'll call it script B de Rham plus.
When you speak of base of group and for which topology?
For the pro-étale topology.
So it's,
they're really, yeah, these are very non-Noetherian things. So there's this sheaf B de Rham plus of U, and well, the situation is a lot like what we saw over a point. It maps to the completed structure sheaf. The kernel of that map is an invertible ideal sheaf. And if you invert that invertible ideal sheaf, you get a bigger sheaf, which I'll just call B de Rham. And now, there's a basic calculation that we can do here. So let me call this map, what's the usual name of this map? Nu? I always forget.
One of them is new.
Nu. Okay, so you have this sheaf of commutative rings on the pro-étale site, script B de Rham. And so calculation, I'm not sure who to credit this to. Maybe in this language, probably Schulze, but I think it really goes back to Faltings. That Faltings figured out how to ask the question to which the answer is the de Rham complex. So the claim is that if you form this push forward, what you get is the de Rham complex of this analytic space. And moreover, this is not just true at the level of sheaves, it's true at the level of the filtered derived category. This B de Rham has a natural filtration by powers of the ideal sheaf on B de Rham plus, and that corresponds on this side to the canonical filtration on the de Rham complex by its subcomplexes of differential forms of, we put some bounds on the degrees. Oh, sorry, this is wrong. All that business earlier about adding this variable u was so that I could make this statement that if you add this extra parameter u and do this calculation, then what you get is the de Rham complex. Okay, so what is this? So let E be a complex two species. X. Well, I can take E and I can tensor it. I can restrict it to the pro-equal side of the analytic space. And I can tensor it with this de Rham sheaf. I think there's a completion involved in this tensor product. And I can push this down to the analytic space. And whatever I'm going to get, oh, I'm sorry, I need to add that extra parameter u. Whatever I'm going to get, it's going to be a module over this, whatever the analogous construction when there was no E. So this is going to be a filtered complex. The filtration comes from the filtration of B de Rham by powers of its ideal sheaf. In the filtered derived category, this has an action of the de Rham complex of X. Let me tell you something else that has an action of the de Rham complex. The de Rham complex of this analytic space, it also acts on the structure sheaf of the analytic space. And it doesn't just act on it, it maps to it by quotienting out by differential forms of degree greater than 0. And well, this O has a commuting action of the ring of differential operators on the analytic space. And I want to use these commuting actions to convert this into a D module. So now let me just give a definition and then I'll end the talk. So here's the definition of RH of E. It's defined to be what you get. Well, this is the analytic version of the Riemann-Hilbert correspondence is what you get when you take R-HOMs in the world of filtered omega star modules. Superscript to indicate I'm doing this in the filtered world. For omega star xn OX into the lower star of this B de Rham brackets U tensor by E. Now, this OX is a left module over the ring of differential operators. When I HOM over OX, it becomes a right module over the ring of differential operators. And this is a model for the normalized version of the Riemann-Hilbert correspondence. It lands in right D modules. And this is the construction that it really takes perverse sheaves to things that are in degree 0. All right, I think I will stop there. Thank you. Questions?
You see, you also take perverse sheaves to just degree 0.
Yes, so that's in my list of claims that this is a wonderful thing to do. That should have been one of the wonderful things about it.
What is, sorry. I did not hear what is a wonderful thing that should be on that list?
So one of the features of the classical Riemann-Hilbert correspondence is that it takes perverse sheaves to algebraic D modules that are concentrated in degree 0. Right. And the claim is that this construction has the same property. Okay. And moreover, it's a little bit better than that because this produces filtered D modules. And the fact that it lands in degree 0 is not just true after you forget the filtration, it's true for the associated gradient of the filtration.
Can you repeat the last step? How do you get the U module structure out of this Omega structure?
How do you get, right, so just a general bit of formalism, like if I'm in some, here's a formal setup. I have two rings that are have commuting actions on some module. And then maybe A also acts on some other module N. And then I form hums in the world of A modules from M into N. So now A doesn't act on anything anymore because I've used up the A actions, but B is acting, let's say, well, here's the B. It actually has a left action on
Oh, I see.
O, and then when I hum into something else, that becomes a right action. Yeah, so maybe, so there were a lot of failed attempts. So after Schulze wrote down construction for de Rham local systems, Bhargav and I had an infinite number of conversations where we tried to do something like this by a formula that would specialize to exactly the construction that Schulze was writing down. And things weren't making sense, or we weren't coming up with good constructions. And this is not exactly the construction that Schulze writes down. This is what you would get if you took his construction, which produces a left D module, and then converted it to a right D module. And somehow if you tinker with the construction to try to make it produce a right D module instead of a left D module, then everything falls into place much more easily, let's say.
How does the Omega star act on the O?
It maps to O. So these are both commutative rings, and this is just projection onto GER0 of the Hodge filtration.
But the Omega star is also like pull back and push forward or to the proton, or is that?
Sorry, say that again.
Sorry. So there's also this thing that if you push from the proton, you get this Omega.
If you push, yeah, Omega star of Xn. Claim was that this could be recovered as R nu lower star of this sheath B de Rham, as long as you add this extra parameter U.
Also, the map is not from like a junction; it's just from like forgetting about it.
No, the map is visible there. So this B de Rham, well, sorry. So first B de Rham plus. So this is a filtered isomorphism. So if you want to see, fill 0 here is the whole thing, and fill 0 here is what R nu lower star of B de Rham plus. And so B de Rham plus sits inside B de Rham, and it also projects onto O hat. And this map, when you take R nu lower star, is the one that produces this map here. So if you want to produce not a filtered D module, but the associated gradient of that filtered D module, there's an easier version of this construction, which is just, you'd never think to write down this ring B de Rham, and you do everything with the completed structure sheaf.
When you speak of module structure, how do you work into the half category?
Yeah, I view it as a symmetric monoidal infinity category, and then there's a good theory of commutative algebra objects, associative algebra objects, modules, and so forth. Probably you could do it in some more concrete way, but I'm not tempted to try to.
Is there an analogous story? Well, not exactly analogous. Is there some story if you start over like an algebraic closed field?
Yes. Isn't your thesis about that?
Not as far as I'm aware of.
So maybe I should say, so I gave a lot of credit to people at the beginning, but I didn't give credit at the end. But Bogdan's thesis is a crucial component of this story. So one of the claims here is you do this construction and you produce something that has an action of the ring of differential operators, but how do you know that it has any finiteness properties at all? The claim is that it produces regular holonomic D-modules. How do you even see that it produces coherent D-modules? And the claim is that, first of all, that coherence is something that you can test before you do this RHOM procedure. That you can just test by studying this object. And so this object is a filtered module over omega star xn. So if you look at the associated graded level, it's an O module. And the claim is that that O module is actually coherent, at least under the assumption that E is weakly Hodge-Tate. And that claim is tested by, or proved by proving something analogous over, not for your variety over K, but your variety over C. And the essential input that gives you the finiteness there is your thesis.
Okay. But you there should be a prediction that it should produce a Higgs bundle over C, right? Or
yeah, well, it produces something which is maybe not canonically a Higgs bundle, but locally, after making some choices, you can identify with the Higgs bundle. And yeah, I mean, that's what happens at the associated graded level. Well, when you're over K, you produce exactly a Higgs bundle when you pass to the associated gradient. And there's something that replaces that over C.
okay.
Sorry, but we don't know anything about it being a bundle, right?
We don't know any.
Like it's a
Right,
something
the
that has
question,
Higgs field on it, but there's no finiteness.
sorry, if we started with something that was only defined over C, yeah, then we, right, like, so I mentioned that you get regular holonomic D-modules out of this. An even better statement is you get regular holonomic D-modules with quasi-unipotent monodromy. And that's something that you should definitely expect because the QPA tall sheaves, when they're defined over a discretely valued field, they have to have quasi-unipotent monodromy by a theorem of Grothendieck. But that's something that you would definitely lose if you were not in an arithmetic situation. You can write down sheaves with much more pathological properties, and we don't know how to prove theorems about those sheaves.
Let's thank Jacob again.